The next formulas we need to deal with an object that doesn't have a constant speed, which we can use then as our average speed. It's what happens with an object that is accelerating. So we have a couple of different formulas to look at acceleration. The actual definition of acceleration as a formula is this. In terms of the numerical acceleration anyhow, at least in terms of the acceleration that is changing the speed, because once again, acceleration can change either the speed or the direction or both. This is the formula that tells us how the acceleration changes the speed. So once again, just in terms of what all of these abbreviations are, the A with the line over the top is the average acceleration. And to be very honest, after this little explanation, I'm probably going to drop the word average, excuse me, because as an object is accelerating, without a bunch of calculus, we really can't do too much with the algebra level with accelerations that keep changing. So we're going to assume pretty much in all of our problems that the acceleration rate is about constant. And so like the velocity thing, if we have a constant velocity, we can use the average velocity formula. Here, if the object is constantly accelerating at the same rate, overall it's going to be an average acceleration. So in the formula, I will put an A with the line over the top to remind us of that fact, but I will probably just drop the word average acceleration. Once again, we will use this for problems that say constant acceleration of, and then give us a number, or even just say acceleration of, and give us a number. So in that case, if we're looking at what's going on with the velocities, we'll get to that in a minute, and the acceleration, this will be the formula. Now in terms of velocities, we do have a couple of special symbols for this. The velocity is always v. Right? The average velocity was v with the line over the top, once again borrowing from kind of the statistics notation. Here, v0 means velocity at time t equals 0. And that's another way of saying initial velocity. We are assuming at any point in time if we're measuring stuff, right, initially we're going to set our stopwatch to 0. I mean, it could be that we have some sort of problem where we're looking at some motion like 5 seconds into the motion or something, but generally our initial velocity is going to be where our stopwatch is set to 0. So we're going to say that v with the 0 is an initial velocity. On the other hand, the other velocity is labeled v with a little t. It's called a subscript, so it's sometimes read v sub t. This is the velocity at time t equals something else. It could be, the problem says, what is the velocity after 5 seconds, after 3 seconds, after 2.7 seconds? And that is what this time is. So it's just some time after the initial time, and the velocity at that time is what we're labeling v sub t. It's also just called the final velocity. So that's another word, another way of describing this v sub t. And you'll see it written both ways, kind of depending upon what the problem and what the author has decided to how to describe it. Little t, once again, is the time interval. So this is the time interval it takes to cause this change of velocity due to whatever the acceleration value happens to be. So hopefully, obviously, the only time we're going to use this formula is when we do have some sort of an acceleration. And it's when we're looking at how does the velocity change throughout some period of time to give us an acceleration. So what type of problem might this be? Well, it might be as simple as we have an acceleration of 3 meters per second each second. And you'll notice when we write acceleration units, there's always some sort of a velocity unit on top divided by a time unit in the bottom. So there's always going to be 2 time units. One distance per time for the velocities, and then another time down below. So if we see something written like this, generally, we put the 2 seconds units together and call it 3 meters per second squared. I know it's confusing for some people because as soon as they see a squared, they also want to square the 3 when we start doing math. That is not what we do. The squared is just on the seconds, on the units, and it's read 3 meters per second squared, but it really means kind of this reverse up here where we're going, changing speed by 3 meters per second every second, or 3 meters per second each second. We can also have acceleration units like 5 miles per hour per second. So that means we're going to be changing velocity or changing speed by 5 miles per hour each second. If we do it and so usually this is the way it's written because mph is just kind of the standard way of writing miles per hour. On the other hand, if we were doing 10 kilometers per hour per second, that means we're going to be changing velocity by 10 kilometers per hour each second. Sometimes the hours and seconds are put together and it'll look something like this. 10 kilometers per hour times seconds. The hours and seconds are both below the per or divide line, and so rather than being seconds squared like this, it's just hours times seconds. But this still means we're going to change velocity by 10 kilometers per hour each second. So I know the acceleration units can somehow look a little messy, but in the end it's always some sort of velocity changing in some unit of time. So let's go back to our original number. Let's say that is our acceleration value. And so my question is, what time is necessary to change velocity from 35 meters per second to, let's go 48 meters per second? Question mark. Assuming we have this acceleration. I mean, that is given. So we have two different velocities here. The first one is what we label our V0, and our second was what we label our VT. So we have our initial velocity and our final velocity. Right, so going up to our formula, it says acceleration is the final velocity minus the initial velocity over the time interval. So once again, putting the numbers in where we know where they are. 3 meters per second is the acceleration, and that's going to equal 48 meters per second minus 35 meters per second over the time interval. And like the last problem, when we have a fraction, we'll actually put a fraction on both sides, and we'll cross multiply. 48 minus 35 is 13 meters per second, equals 3 meters per second squared, times t. Do the algebra. And once again, we have a situation where the meters are going to cancel. This is per second, and this is per second per second. Right, so the per seconds are going to cancel out, and once again, this extra second factor, since it's on the bottom, is going to flip up to the top, and we are going to have 4.3 repeating, right? 4 1/3 seconds is the time. So this is kind of a typical problem to use this formula. Now there is a separate formula I wrote on the board which is very similar to this. It basically just does some algebra by multiplying both sides times the time and then moving the other velocity over. It basically says that the final velocity of an object, if it's accelerating, let me slide this up and over a little bit, is going to equal the initial velocity plus the acceleration times the time. And these two formulas are mathematically identical to each other. Right? It's just doing a little algebra to derive one from the other. So either of those will work for any of these problems where we're looking at velocities with acceleration and we know the time it takes, or we're looking for the time it takes to cause the change.